This is a manufacturing story, how we go from raw material to a finished product, the B200 balancing ring from Kinetic Precision. We've been making these for several years, and in order to achieve efficiency in Op 1, we decided to go with the Mitee-Bite VersaGrip system, except their grippers were holding the part right over the vice jaws where we had to drill our holes. So we designed a gripper which elevated the part and gave us enough space to drill the holes and finish them. The gripper was a success, except in the first generation, we screwed up the heat treating. So this time around, we've improved that. We made some slight dimensional changes, and we got rid of the old ones expeditiously. And now, the gripping tail. You know, the thing about these Micro 100 tools is that they're so fine, and this isn't even the smallest one they make, that it seems like they're not doing anything. But then you look and you realize, oh no, they're doing something. They're doing something really nice. What's important is these have to get heat treated. So if we come over here to the heat treating department, and I know what you're thinking. You're thinking this is the grinder department. It's also the heat treating department. I got reminded by one Robin Renzetti that I should have a fan for my air quenched A2 tool steel. So I got this fan, and all I did is attach an aluminum bar to it, so it's kind of stable. And I'm going to turn it on, and you can see that it, in fact, works great. And this is going to be where we cool the A2 parts when they come out of that oven, and they will cool down to room temperature. So that's not what I want to show you. What I want to show you is this fan. This fan, at first glance, looks mighty boring. And it looks like it came out of some surplus bin. And you know, in some respects, it did. But actually, this fan has some significant history. Look up on Google Lisp machines, L-I-S-P, Lisp machines. This was some of the earliest computers that look like the computers you take for granted today. And this was the cooling fan off of either Cadre 6 or Cadre 7, that's C-A-D-R, Cadre 6 or Cadre 7, that came out of MIT. And a buddy of mine had these two mainframes. It was a it was a 6-foot high rack, 19-inch rack. That was the computer. And he gave them to me, and then eventually I had to disassemble them, but I kept a couple of pieces. This is one of the pieces. So a very, very storied history in this fan, which is going to cool my parts. So we finished turning the parts on the lathe. You can see the upper 4 parts in the upper right corner were rejects. We used those as heat treating samples. We ultrasonically cleaned the parts. One of the goals was to have them be squeaky clean going into the heat treat envelopes. Here they're cleaned and dried. They really look good, don't they? They look bright and shiny. And we started packing them into a stainless steel envelope. I took the tungsten out of my TIG torch and proceeded to purge the envelope of oxygen by filling it with argon. You can see here it's tipped up a little bit. We're treating the argon like a liquid because it's heavier than air. And finally, we sealed it up, and it went into the heat treating oven. This is the hot shot that you see on the left in the pictures. Here it is, programmed and ready to go. The program for this is about 5 hours long. It starts with a 1200 degree preheat and a 1400 degree hold, and this is the result. You can see it's on the rack getting air cooled. The pouch, if you look at the inside, was shiny. It had a little gray to it, and that's about it. After we brought it back to room temperature, I loaded them up, and they went into liquid nitrogen overnight. After liquid nitrogen treatment, they came back to room temperature, went into the smaller of the hot shots for a dual 500 degree temper. Here you can see we're in between the 2 cycles of 500 degrees. And this is how they came out. You could see a little bit of stoning marks on the top surface. That was the initial reference surface that we used for grinding. Top surface down, we ground the bottom, got a beautiful finish. And when that was done, we flipped them over and we ground the tops. There was an intentional 5/1000ths left on the top surface, which we took off in grinding. And that's how the heat treating went, and it came out awesomely well. Here you can see the hardness data we took at each stage of the process. So taking it from the top, when the parts came out of the oven and we did the air quench only, they were coming out at about Rockwell C67. The liquid nitrogen treatment didn't seem to change that hardness. That's fine. And then after a single temper, they came out at about Rockwell 58. That particular measurement didn't inspire confidence because it changed a little bit around the part. But after the second temper, we started measuring a solid Rockwell C60. The fact that the hardness came up in the second temper is interesting. But that's how we left the parts, Rockwell 60, and they seem to be behaving quite nicely. So we have a little bit of a problem. We made the grippers, and they came out great. And the heat treating came out great. We ended up at Rockwell C60, which is kind of where we wanted to be, maybe a little higher than we wanted to be. We ground top and bottom, and they look fantastic. The problem is they were a little too big in diameter. So the goal was 750, and we're at 752. This is suboptimal. So they're actually not fitting in the Mitee-Bite jaw. Can't hardly blame them. And what we're going to do is we're going to grind the outer diameter down to, well, probably 749.5 and call it a day, and then they'll be usable. The way they work is they screw into the jaw with a single screw, okay? And this provides the gripping surface for our part. So our part goes in, it sits on the shelf,
okay, like so, and gets gripped. So follow me along while I set this guy up for rotary grinding, and we'll take this OD down just a little bit. Stand by. Well, good afternoon and happy Saturday. I'm at the mill setting up for B200 balancing ring action. If you don't know what that is, go to the website and read up about it. It's under rin.gg for ring. Anyway, we're doing really well. We got a check mark over here. This station is ready to go. We got a check mark over here. This station's ready to go. No check mark here yet. You may recall we made these magnificent grippers. Well, this is where those grippers go, except there's one problem. A silly little problem of 1/1000th of an inch. And I think what happened was the oxide layer growth was enough to put this out of spec. So I'm gonna pop this onto the grinder as soon as the grinder is available, and I'll show you what I'm gonna do. So as soon as the grinder is available, I'm gonna use this tool, okay? And this tool will hold on to that part, okay? And then this goes into my spin jig, and I will rotary grind these to get them to exactly 750, down from about 752, which is where they're at right now. And it'll make them look a little nicer, but that's where we're heading. So this isn't going to be ready today, but that's okay. I'm not ready to start cutting metal today. So a little later, we'll do a video on rotary grinding. Take care. So it's not obvious from watching me stone the table, but there were two burrs in the middle here. You might have heard them, and you're getting a lot of feedback from the feel. And those burrs are now gone, and I can feel that there's nothing unusual on the table. Same thing, we can feel if there's anything going on. So I felt something in here, so I gave it a little extra time, but it's gone. And that's ready to go. So this spin jig has a V-block that's integral, and this V-block can move up and down in these tracks on the face. We could also jump it to different holes. So this has a lot of motion. And then there's a clamp that goes on top to clamp the work in. This is how we're going to use it. This particular spin jig also has a 5C collet capability, which we're not going to use. And yeah, let's get this thing set up. So the reason we're not using the 5C collets is because our little tool here is 848, 849. So we're just going to hold our tool in the V-block, and it will be ready to grind. So it's going to look a lot like that, and we're going to be working right here. And everything's going to be moving here, so We'll do that once it's on the grinder. So if it's not obvious, we've set up the wheel. The wheel is previously balanced. We will be dressing it. We set up the nose, and we already have stoned the chuck. So we're going to get the spin jig, which we've already stoned, and bring it over. So we've plugged in the motor. We want to make sure that we are to the right of this knob so that when the head comes down to dress itself over here on the diamond, that it misses the spin jig. So it turns out that's good enough. It also might not be obvious that the motor needs to get plugged in, so we've routed the cord around the end of the table. So for the purposes of the video, I've turned off the magnet, and I'm going to spin this guy around, and we will turn on the magnet in this weird configuration just to give us a place to work, because I want to show you how this goes together and how we adjust it. So I'm loosening the two Allen screws that will allow the V-groove to slide up and down. See that? And we're going to observe if we think we have to go further down. I'm not sure. Oops. Yeah, we're going to have to go further down. Also, we're probably going to have to move this to the shorter clamp screw. It's always something. So I'm using a nylon acorn nut as a pad. I'm using a brass nut to lock it. And I found that to be a pretty nice combination. It always pays to have a local hardware store. Very local. Yep, that's going to work. So I like the nylon acorn nut because it gives a little cushioning and actually a little spring action. Voila. Let's see, will that spin? Yep, it will not hit the chuck. Okay, good. We are rolling. So it looks like we do have to move down one on the screws. So this is a screw, a plastic washer, and then a flat washer. And it's stainless, which is why it's not sticking to the magnet very much. There we go. So I'm putting these in just with a little bit of finger torque just to hold it, because we're going to be tapping it around. Okay. It's a little too much. So I'm looking here, not here. I'm looking right here. And I'm using the Mark I Mod 5 eyeball. And that's about the limit of the Mark I Mod 5 eyeball. All right, we did a rough centering here on this boss, and it's not great. It's within about 5/1000ths, but we don't really care because we're going to be tapping in the part. So let's move over to the part and do that. All right, so now we're going to tap in the part. Now the part is really obviously out. So I'm going to find the high spot. I'm going to move it 90 degrees so I can tap it a little bit. I'm going to tighten that up a little bit more. So if we find the center of the extremes, you know, it doesn't have to be perfect, just approximately. We can go to the high spot. Yeah, 90 degrees out, right? And now we can go to the low spot, which is right there. And I'm just going to tap from the bottom. Boom. Okay, there's the low spot. Oops, I'm sorry, that's the high spot. There's the low spot. Oops. It's looking better. It's looking worse. And that would normally be good enough. We're just going to give it a little bit of so that's probably 1/10 right there. Note that this is not a tenths indicator. This is a half thousandths indicator. So I'm actually reading it finer than it's intended. And I think we're gilding the lily here. Okay, that's good enough right there. So we're going to tighten that up. There's a washer under it. That's it. So now we're going to grind this cleverly color-coded surface, and we're going to take that down. So we're going to do a micrometer measurement. Fun fact, index card, it's about 8 thousandths. But I'm closing the micrometer on the index card and just pulling it out. And that's my cleaning routine. There we go. So on the calipers, these were coming in at 752. And this is 75185. Okay, so that's about right. And this guy's ready to go. So I'm going to spin him back around. I'm waiting for the demag to finish. Now notice I don't lift him off the chuck. I just spin it around. I don't want to get any particles underneath. I'm going to put my 2 spacers on there. And actually, I'm looking at it now. It's like I want more spacers, so I'm going to grab some more. So I'm actually going to bring this guy in a little more. So I know it's hanging off quite a bit, but for us, it's just going to be fine. Once again, I'm pushing on the back. I'm pushing on the spin jig and all the spacers, and it is fine. So I'm taking off my bar, taking off my spacers, turning on the magnet. So the spin jig is solid on the table. Our part is indicated up, ready to grind. Now I'm going to have to true the wheel. So I'm going to go over to the control and tell the control which wheel it has, and then I'm going to put it through an automatic truing cycle, which I don't think I've ever shown in detail. Let's go take a look at what that looks like. Okay, we're at the control, and this is how we set up for the wheel. So we're going down here to dress setup, dress form select. Actually, before we do that, we have to go to dress management. So right now, the numbers in the machine are for our 5SG wheel, so we're going to save those. Okay, and we're saving to number 3. Input. May I save as G wheel data? Yes. And we're done. Now I'm going to load the white wheel 38A46H, and I'm going to say read number 2, input, correct wheel, execute, and it's done. So now the machine knows that it's on that wheel, okay, which we've been tracking in the machine, so it's ready to go. Now I go back to the dress menu, dress form select. I tell it, take off the schmutz. On the dress form page, we say I want a straight dress. Now there's all sorts of dressing we can do. We're not doing any of that today. So straight dress, select. These numbers, we don't change them because it already knows the numbers because it's been using the wheel. And we say dress. Okay, and here we can set up our dress. I'm going to take 2 passes on the diamond at 30 inches a minute, 1/1000th of an inch per pass. And that's a middling pass, that's fine. Nothing else. So that's what we want. We say, I'm not sure what they're trying to say, TRANC period. Translate, Transylvania. We hit that and it says data was transmitted, push a cycle start key to perform dress. So this is ready to dress. I'm not going to do it quite yet. Okay, in an effort to keep the grit in, I'm just going to do a little jankification here and keep the shield on. Okay, so what you're going to see is you can see the wheel come down and it will dress on the back diamond, and let's do it. Turning the wheel on. So this is a aluminum oxide wheel. We dress at the same speed that we grind at, which is 3600. Especially now, this wheel has gotten a lot smaller in diameter, so we're giving it all the beans. So it was safe. We double checked it. My eyeball was off. It looks good. So let's run that one more time. I want to hear a little bit better grind. Nice. So we have a few concerns here. Clearance from this shield to this nut, clearance from the front. So we're going to spend a little time checking that. The first thing I'm going to do is I'm going to raise this shield to get that out of the way. That looks good. The top of this nut is going to clear this. That looks good. And now I'm just going to check. Actually, the top is not going to clear this once we come down. So we're going to do this shield open. Kids, don't try this at home. I'm going to bring this down within, I don't know, about 30,000ths of the part. Yep. All right, so that's what it has to do. I think we're going to be fine. Okay. And now I'm coming up and I'm looking from the top and I'm getting it centered up. Now, we're not going to be moving the table once we start. Okay. In fact, once we get this thing centered up, I'm going to move it very slightly, maybe to the left, but that's about it. And I'm going to actually disengage the hand wheel and turn off the hydraulics. That's done with the little lever on the front. So the table is where the table is, and that's it. Okay? So I'm going to come in and I'm going to go until I have a little space before the major diameter on our arbor, and I'm going to go over to my front panel, to the position screen, and I'm just going to set that as Z0. Okay, and for the, I'm going to set Y0 and X0. So now I have a reference. And now I'm going to come down. First I'm going to turn on my, my motor, right? I'm going to spin this once by hand, make sure I don't hit anything. And actually, I'm just missing my coolant NOS. So I'm going to pull it down, get that out of the way. Now we're good. All right, low speed. I'm going to turn it into the wheel. Not that it really matters. And a bit of a low speed. Okay, I'm going to bring it down just a touch off. I'm using the light between the wheel and the part, and I'm waiting until that light starts to dim. Okay, and now I'm switching to the superfine downfeed, which is 0.1 tenths, or 1/100,000th of an inch per click on the hand wheel. I'm going to speed this guy up a little bit. Okay, I heard contact and I see some little teeny sparks. So I'm going over to my control and I'm setting Y origin. I'm coming off the part. I'm going to come down 3/10. And I'm coming on the part manually. Speeding up a little bit. And just feeding in gently. As soon as I see the part clean up, I'm going to continue in. You can tell that my arbor is not as accurately centered as my part. And I'm just going to peel out. And I'm going to stop the motor for a second, and I'm going to give you a picture of the finish that we're getting. Looks great. I'm going to come down to another 3/10, so 0.9. I'm sorry, 0.6. And I'm going to go in manually. It'd help if our motor's going, right? And I'm judging my speed of infeed on the sparks. I don't want a whole bunch of sparks. Looks good. And coming back out. Coming down another 3/10. Do I have to be this this crazy? But no, I'm trying to be conservative here. Coming back out. That looks great. And now I'm going to finish off coming down 1 more tenth to a total of 1/1000th of material removal. And we're done. Now, one of the things you're taught if you learn how to run a grinder is you never turn off the wheel. So if you're running on a VFD, which this qualifies as a VFD, that has acceleration and deceleration, and you have this very slow acceleration and very slow deceleration, you're not going to shock the wheel. In the old days, when you slammed on the 3-phase power and that wheel fired up, you were shocking the wheel, and they were worried that you would move the wheel off center, and then you dress the wheel, and if you do it again, you've lost your center. but we're not worried about that because of that slow acceleration. So the wheel's off, and let's measure it. This is going to be mighty hard. Well, it might not be that hard to see. I don't know. Let's see. Open this up. Okay, nice. 7493. Perfect. So I like that, and I think we're going to keep it. So we're going to remove this, do a trial fit in the actual vise, and see how it feels, and we're probably fine. We're going to leave the machine set up exactly like it is. We're just going to come in here and remove our part. Now you know why it's nice to be able to turn off the wheel. Look at that. I'll take it. That is totally acceptable. Okay, so this was super acceptable, really nice, and we're just going to go for it. So washers have two sides, right? It has the side that curves down, and it has the side with the lip. So we're putting the curvy, smoothy side toward the part so it can move around on the washer. You know, are there quicker tricks to doing this? Probably. Does it matter that I'm super concentric? No. Is it good to practice a technique? Yes. So that's just a little finger tightening on that. So I can't emphasize enough that, you know, we're doing something here. We're not on the clock. We're doing something a little more accurate than it needs to be. And there's a reason for it. You're training your hands. You're training your eyeballs. And I'm calling that good enough. So another trick is we're going to leave our indicators joints all set up and not change them. So that'll speed things up a little bit. So we're not going to change anything. We came down 1,000th. We're going to do it again. Grinding wheel on. I brought the wheel higher. I got my motor on. I'm visually checking to see everything's cool. Okay, I'm going to come down. I'm watching my my DRO and listening. And contact. I heard something. So it says I've got 1.8 tenths to go. But I did contact. So now I'm going to do the same dance. I'm going to come down 3/10 approximately. we'll take it. So do you see where the sparks are? So we're getting wheel wear because the cutting is happening further from the leading edge of the cut. Do we care? No, because we have plenty of wheel that is not worn. I am using the power feed. And I'll give you this view again. And we are done. Parts made, well within the tolerances we need, but more importantly, we had some fun and practiced some techniques of getting those tight tolerances. The parts came out just awesomely well. And I did measure them as they were coming off, and they did, I mean, part to part, they were like millionths. We did see wheel wear. It didn't matter. When the wheel wears on that leading edge, as long as the trailing edge traverses the entire part you still have accuracy left. So we did the job. We're gonna go over to the mill. I'll show you how these parts are used, and we'll wrap it up. Okay, we're over at the mill, and you can see that this is the setup for making the B200 balancing rings. So here's where these parts get used. This is the VersaGrip by Mitee-Bite. Let me bring you in closer. So I'm a big fan of Mitee-Bite, a New Hampshire corporation. They make a nice product, and we use the VersaGrips, and we also use some of the other grippers. But we had to make our own gripper because we needed to elevate the part over the jaw. These are their jaws, and they work quite well. But the thing to know about their jaws is they're intended for the part to register on the top of the jaw, and then the gripper just grips, like so, okay? However, the way, for the geometry of the B200 rings, I need to be drilling and tapping very close to where that jaw is. So I designed this gripper to raise the part up off the jaw. So let's see how that looks. So here's our new gripper, and you can see that now the part is held up off the jaw, and I'm able to do my through operation and still have a good grip. So let's put some of these guys in and show you how that looks. So we're going to be using this torque wrench in our process so that we don't over torque this and damage our teeth. In the last generation of grippers, we ended up with a poor heat treating and tried to fix it, and that resulted in having some parts crack. So here we're showing that we found a very nice torque wrench that is going to be married to our vise, and we will now be torquing the vise down under control to prevent any issues. You can see where the tooth is biting. Okay. There you go. That's not going anywhere. Let's crank it up to 70. See what that feels like. I kind of like that. So 70 foot-pounds seems completely reasonable. I think we could accept 70 and run with it. Well, this looks good to me. 70 foot-pounds looks good to me. Let's write it in our notebook. 70 foot-pounds. We could put away our gripper tools. There we go. These are the old grippers I made, and they were a heat treating disaster. I think I'm a lot smarter on heat treating now. We got a lot more grippers to go. We could use different configurations, but this station has earned its check mark. 70 foot-pounds is the magic number, and we can now clean up and get ready for production. So let's talk real quick about setting this thing up for production. By the way, I played around a little bit, and I decided 80 foot-pounds is good. So we're going to go to 80 foot-pounds. And one of the things that I wanted to make sure I got right was how to put this handle on. What do I mean by that? So when this guy is torqued, right, here's 80 foot-pounds. Click. Okay. So when this guy's torqued for 80 foot-pounds, this handle is sticking up. And that's good. And we're ready to run. When we go to loosen it, this handle goes down, and it is just loose enough to remove the part, and we could put in a new part without a lot of fumbling around, okay? So that's how I set the handle up, so that the handle is sitting like that, which is sort of a natural position because there's extra mass here. And then when we go to tighten it, we can come up, touch, put our torque wrench on it, click, and we're done. So that's the setup for production. I think it's important to point out that this handle position is actually important, so that the operator is going to open it like that and be ready to go. Well, I'm out of excuses. I've got to make B200 balancing rings. I've got orders. There's our grippers. Here's our heat treat testing items. That was very instructive. We came in at a Rockwell 60. The grippers are a new design. They're slightly different than the old grippers. The old grippers are here, and they are becoming scrap metal. But they did their job. They went through you know, a fair number of B200s, but these new ones are going to be just spectacular. So thanks for hanging in there. We learned a little bit about heat treating. We learned a little bit about rotary grinding. We learned a little bit about the lathe guy not checking the print. Yeah, you. Have a good one.
Everybody wants to talk about the grinding. Nobody ever wants to talk about the cleaning.